seminars, which will, as we counted, about 13 seminars will be in this semester. So the first person invited is Jarosław Kopiński, who is now working at the Center for Theoretical Physics. I don't know what is this dx. So perhaps you will explain this. And he will talk about mass inequalities. So in fact, the subject, not exactly this title, but the subject of mass inequalities was the subject of his PhD thesis. And so he's still interested. Okay, so please begin.
Okay, thank you for this introduction. So as Professor Taflo mentioned, I will be talking today about a new spinorial approach, a la Witten actually, to mass inequalities for asymptotically flat initial data with black hole inner boundary. So this is a joint project with Juan Valiente Cron from Queen Mary University of London, and is available under the presented archive ID. So I will start this talk with a short introduction to spinorial formalism, which is at the spinorial formalism in GR, which is at the core of our proof, and with the so-called space spinor formalism, which is basically a 3+1 decomposition in the context of spinors. Then, since I want to discuss initial data with inner boundary, I will also mention the 1+1+2 decomposition of spinors, which is adapted to this setting. And lastly, I will move to discussing the proof of the new bound on ADM mass, which is based on a second-order spinorial equation, which we call the approximate twistor equation. This equation is, as I mentioned, is solved on asymptotic data with inner boundary. Okay, so I will follow conventions and notations which can be found, for example, in Penrose and Rindler book. So the signature of the 4-dimensional metric will be plus, minus, 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 which is somewhat more convenient to use when talking about spinors. I will use abstract index notation, where uppercase letters will denote spinorial indices and lowercase ones will denote tensorial indices. I will also talk about the components from time to time, and to distinguish the component indices from abstract index. In the abstract indices, I will just use boldface letters. So a spinor for me will be just an element of some 2-dimensional complex vector space, sigma, which is endowed with symplectic form, so antisymmetric, bilinear, and non-degenerate function, which goes from 2 copies of sigma to the space of complex numbers. The usual notation for a basis of such space sigma is that its elements are denoted by omnicron and iota, and since they form a basis, they have to satisfy relation 1. So those basis elements, omnicron and iota, can be used to decompose any spinor kappa from sigma into its components kappa naught and kappa 1, which are obtained just by evaluating the symplectic form of all on kappa and the appropriate basis element, as can be seen in equality 2. So the higher valence spinors can be obtained in a fairly standard way with the use of multilinear map. So for example, if you want to introduce a spinor high of valence 3, you can do that as can be seen in relation 3, where sigma star is just a dual space to sigma. The action of the symplectic form of some 2 spinors kappa and phi is usually denoted in terms of so-called Levi-Civita spinor, or simply epsilon spinor, as can be seen in 4. And since we are in dimension 2 and the symplectic form is antisymmetric, then epsilon spinor is defined uniquely up to scale. And this object can be used here to actually construct a correspondence between spinor space and dual space, or to say it otherwise, to move the index up and down. Because if we have some spinor phi from sigma, as in 5, then if we contract it with epsilon spinor, we'll get a corresponding element from sigma star. And conversely, if we firstly define the inverse spinor to the epsilon spinor, which I will just call epsilon with upper indices, as in 6, which satisfies a normalization relation with Kronecker delta, then this inverse epsilon spinor can be used to construct a similar correspondence, but going the other way around. So from sigma star to sigma, as can be seen in 7. So since I will be talking about the relation between spinors and tensors in a moment, I'm also going to need a complex conjugation. So for any element kappa from sigma, we can define this complex conjugation, which I will denote here by bar. This complex conjugation lives in the conjugate space sigma bar, as can be seen in 8. And to distinguish the conjugate indices from the standard indices, I will denote the former one by a prime. Yeah, so kappa A prime lives in the conjugate space sigma bar. And so just as the epsilon spinor can be used to move index up and down between the spinor space and its dual space, if we consider a complex conjugation of this spinor, as in 9, then this object can be used to construct a correspondence between space sigma bar and its dual space. Now, just to give you a quick example of why to use spinors, let me talk about a fairly simple theorem about irreducible decomposition, which on its own can serve to simplify any spinorial calculations in a significant way. So this result says that any spinor is can be completely characterized by a sum of its totally symmetric part and the products of Levi-Civita spinors and Levi-Civita spinor or its complex conjugation with symmetrized contraction of this spinor. So for example, if we have some spinor eta with 4 indices A, B, A prime, B prime, then it can be shown that it's completely characterized by a totally symmetric part, which is the first term on the right hand side of 10. And what's left are just the terms which have epsilon bar in it, together with symmetrized contractions of eta, where of course I use the standard notation for the symmetrization bracket as can be seen in 11. Okay, so now I want to move to the relation between spinors and tensors. And my strategy here would be firstly to construct a spinorial counterpart of the metric tensor with the use of an educated guess, and then extend this construction to any tensor. So suppose that we have a 4-dimensional Lorentzian manifold now, M with a metric G, and we also have an orthonormal tetrad EA, as in 12. And the goal, so my goal now is to construct a spinor which corresponds to the metric. And so this, first of all, this spinor, since the metric tensor is a real tensor, has to be self-conjugated. So it has to be a real spinor. And secondly, this is where this educated guess comes out. Since the metric is kind of a most fundamental tensor on M, then there should be a connection between this tensor and this fundamental spinor epsilon from the spinor space. And we can convince ourselves that the simplest product of epsilon together with its complex conjugation, which is self-conjugated, can be written down as on the right-hand side of 13. And apart from the fact that this spinor G from 13 is self-conjugated, and its trace is equals to 4, which is exactly what we expect from the we should expect from the spinorial counterpart of the metric tensor. So given those two reasons, I will just call the spinor G from 13 a spinorial counterpart of the metric tensor. And to formalize this, the thing that I just said, we can write it as equality 14, where on the left-hand side we have the spinor G, which is a spinorial counterpart of the metric tensor. And on the right-hand side we have tensor. They have the metric contracted with certain symbols, which are called Infeld-van der Waerden symbols, and they they serve as a way to a spinorial counterpart of the metric tensor from the tensor itself. And if the metric tensor is written in the orthonormal basis, then those Infeld-van der Waerden symbols are just 4 2x2 Hermitian matrices, and they are just unique matrix and 3 polymatrices. Of course, there are some normalization relation of Kronecker deltas that those symbols have to satisfy, and that they are just given by 15. And as I said, now I will use this construction of a spinorial counterpart of the metric tensor. This construction can be used to define spinorial counterpart of any tensor. So let's say that we have some tensor T, and then its spinorial counterpart, which I will just call with the same symbol, can be written down as in 16, where on the right-hand side we have the tensor contracted with appropriate number of Infeld-van der Waerden symbols. In particular, during this talk, I will rely heavily on heavily use the spinorial counterpart of the Levi-Civita connection nabla A. So this spinorial counterpart will be just nabla A prime as in 17, and this will be an operator which acts between a space of spinors of valence n and a space of spinors of valence n plus 2 as in 17. And from the fact that Levi-Civita connection annihilates the metric, we can almost immediately deduce that its spinorial counterpart will annihilate epsilon spinor together with its complex conjugation as in 18. Okay, so now since I want to work on the initial hypersurface, let's assume that our manifold M has a space-like hypersurface S with unit normal N, induced metric H, and in Levi-Civita connection dA. And from the spinorial point of view, it's somewhat more convenient to, instead of unit normal, to use the normal with norm 2. So I will do that from now on. So instead of unit normal n, I will use normal t, which is just square root of n, or in spinorial language, the spinor tau satisfies 19. And this spinor tau now can be used to construct a correspondence between the space of conjugate indices and the space of the standard indices. And this correspondence is made just by contracting tau with the prime indices. So let's let's say that we have some spinor omega with both prime and non-prime indices as on the left-hand side of 20. Then a spinor tau can be used to construct its version of omega only with unprimed indices, which I will call a space spinor counterpart of omega, by, as I said, contracting the prime index from tau with the prime indices of omega as on the right-hand side of 20. So there are two basic consequences of this construction of space spinor versions of spinors. So first of all, this construction can be used to define another conjugation, which I will call Hermitian conjugation and denote it by a hat. So this conjugation is constructed from a space spinor, so a spinor only with unprimed indices, in a way which is visible in 21. So the omega hat will be just omega. So the Hermitian conjugation of some omega will be just its complex conjugation, which is then contracted with appropriate number of taus, as on the right-hand side of 21. This Hermitian conjugation is important because it can be used it induces a positive definite product on a space of space spinors. Because if we contract a spinor omega together with its Hermitian conjugation as in 22, then it can be shown that such product is always greater or equal than 0, and it vanishes if and only if the omega itself vanishes. So the second consequence is that the space spinor construction can be used to define a spinorial counterpart of a space-like projection of any tensor. So suppose that we have a spinor VA prime, which is a spinorial counterpart of some one form V. Then we can check that if we construct a space spinor counterpart of V and then symmetrize this space spinor counterpart, then this spinor VAB from 23 will correspond to the space-like projection of a one form tau on one form V on our space-like hypersurface S. Yeah, so so we can construct a spinorial counterpart of, for example, of a three-dimensional metric H, which will be just a product of two epsilons with a symmetrization, as in 24. And we can also construct a spinorial counterpart of the extrinsic curvature of a three-dimensional space-like hypersurface S, which I will call big K. And the spinorial counterpart of extrinsic curvature is given by 25. Now there is a derivative operator which appears in 25, which is not just a spinorial counterpart of the three-dimensional Levi-Civita connection, but instead it's something which is usually called a Sen connection, and I will define we just denoted by a curly D instead of a usual D for a Levi-Civita connection. So this Sen connection in tensorial language is basically a partially projected full four-dimensional derivative of some vector V as in 27. And we can see that in order to obtain a usual three-dimensional connection from the Sen connection, we need to apply a second projection on both sides of 27, which can be formalized by writing the relation between the Sen connection and the Levi-Civita connection, which in spinorial language looks like has a form of 20 equality 28. So we have a Sen connection on left-hand side, and this can be decomposed into Levi-Civita connection and the transition spinor between those two connections, which is just a three-dimensional extrinsic curvature of our space-like hypersurface. Okay, now I will assume from now on that my space-like hypersurface S has an inner boundary partial S, which is a topological two-sphere, and that the normal vector to partial S is rho A. And just as it was with the normal vector to S, I will, instead of considering a unit normal vector, I will consider a vector which is normalized to -2. So, and of course, it's orthogonal to our vector tau, as in 29. And we can, of course, construct a space. If we consider a spinorial counterpart of this unit vector, we can construct its space spinor counterpart, which is just given by 30. And now the goal is to further decompose any spinorial quantities, any space spinorial quantities, into the parts which are basically orthogonal to partial S and which lives on the partial S. And I will just do that by considering simple compositions. So for some space spinor VAB, there exists a good decomposition of this spinor into parts V orthogonal, as can be seen in 31, which is just a contraction of V with my spinor rho, and the part V parallel, which is just the remainder. So probably the most important decomposition for me is the decomposition of this three-dimensional Sen connection, which I introduced a minute ago. So again, this connection can be decomposed in the first term on the right-hand side of 32, which is basically a normal derivative to partial S written in the spinorial language, and the remainder. And I will denote the remainder as slashed partial D, and this will be my two-dimensional Sen connection. This two-dimensional Sen connection, again, it's not a two-dimensional Levi-Civita connection, which now can be denoted as slashed D, but again the relation can be written down, the relation 33, so which says that the two-dimensional Sen connection slashed curly D can be decomposed into the part which is a two-dimensional Sen connection slash D and a transition spinor Q. And surprisingly, this transition spinor is not the extrinsic curvature of this two-dimensional surface partial S embedded into three-dimensional initial hypersurface S, but instead Q depends on null expansions theta plus and theta minus and shears of the inner boundary partial S.
Excuse me, Jarek, if it depends on null expansions and shear, it is extrinsic curvature, but as a two surface in 4 dimensions.
Yes, I agree, but I just wanted to say that it is that the relation between the relation between three-dimensional Sen connection and three-dimensional Levi-Civita connection, so the transition spinor was just the extrinsic curvature, and here it is not the extrinsic curvature of this two-dimensional surface embedded in the three-dimensional initial hypersurface, but it is an extrinsic curvature of this two-dimensional surface embedded in the four-dimensional manifold. I agree.
But if you take four-dimensional covariant derivative and the tangent part of this tensor, then it is splits into internal this kind of relation exists in normal geometry without spinors. So,
okay. Okay, but but the main point here is that we have null expansions appearing here in the relation 33. Okay, so now I'll move to the proof of our mass inequality. So suppose now that our initial hypersurface S is asymptotically flat, but it is asymptotically flat in a specific way, which I will call asymptotically Schwarzschildian, or AS. So the metric tensor has a principal part, which is a Schwarzschildian part, and the remainder, which decays are like R to minus 3/2. And it's the extrinsic curvature of S indicates as can be seen in 34. So as I mentioned in the beginning, the proof will make use of a second order spinorial equation. And the second order spinorial equation will be constructed from a first order one, from a so-called spatial twistor equation, which says that, as can be visible in 35, it says that the totally symmetric part of a three-dimensional Sen connection of some spinor kappa vanishes. And this spatial twistor equation is basically a space spinor version of a usual twistor equation 36, which was introduced by Penrose in 1960s. So now I want to construct a second order equation from 35, and I will do that just by composing this spatial twistor operator with its adjoint. So this construction will give me equation 37, which I will call approximate twistor equation. We can see that basically the first part of 37 is a Sen version of three-dimensional Laplacian, and we also have a lower order terms of extrinsic curvature and mean curvature. Okay. So now I want to solve 37, but with the assumption that the solution has a specific expansion at infinity, given by 38. So I have a principal part with this Schwarzschildian parameter M, and X is just a matrix of asymptotically Cartesian coordinates. And the remainder of the solution, I want it to decay as R to minus 1/2. Or faster than R to minus 1/2. So this specific choice of asymptotic expansion of a solution can actually be used to write down the inequality between mass of my initial hypersurface and some inequality bounding the mass of my initial hypersurface. And we can see it from a following construction. So suppose that I will define a functional I, which is given by 40, and where I introduced a notation. Spinor high is just a partially contracted first derivative of kappa, as in 31. And the first observation first thing which can be said after looking at functional I from 40 is that since it is a spinor which is contracted with this Hermitian conjugation, then this functional is always greater or equal than 0. So the second observation is that we can take 40 and integrate it by parts, use the fact that kappa satisfies approximate twistor equation, and convince ourselves that the functional A can be written only in terms of the boundary integrals, as in 42. And now, since I assume that the solution kappa has the specific expansion, which I talked about a minute ago, the integral over the sphere at infinity will be just 4 pi m, which is the first term on the right-hand side of 42. And the second integral is just the integral over inner boundary. So if we combine 42 with the fact that the function of I is always greater or equal than 0, we'll end up with our mass inequality given by 43. So with the inequality 43, we now have two tasks here. So first of all, we need to prescribe some appropriate boundary condition on our second order, to our approximate twistor equation, which makes this right-hand side of my mass inequality non-negative. And secondly, with this choice of boundary condition, we need to prove that the solution to approximate twistor equation with this boundary condition exists. So if we look at this lower bound on the mass, which was obtained just by this integration by parts, we can see that probably the most natural boundary condition is to assume that this spinor high A from 44, which, let me recall, it was the contracted first derivative of a solution kappa, that it is some spinor, fairly prescribed spinor phi A on the inner boundary. And since this boundary condition 45 is not a usual Neumann or even Rowan boundary condition, we need to check if it satisfies Lobachninsky-Shapiro compatibility condition in order to proceed in our investigation. But fortunately, it is the case here. So now I will assume that my boundary condition is just 45, and proceed with studying the existence of a solution. So now, with this choice of boundary condition, our boundary value problem
Excuse me, but what are these
Yes.
Shapiro conditions?
So basically, you need to take a principal part of an operator and the boundary condition and verify and consider and assume that the solution is a radial solution, and verify if the only exponentially decaying solution is a trivial one. Those are those conditions. Yeah, if the only radially decay radial solution which decays exponentially is a trivial one, then those conditions are satisfied.
And practically, it is possible to verify this condition?
I mean, in this case, yes, because the principal part of the operator is Laplacian, basically, and this. Yeah, and as for this boundary condition, yeah, I mean, it can be verified in this case.
Okay.
I mean, for the usual Neumann or Robin conditions, you don't have to verify, because those are kind of standard boundary conditions. So this compatibility condition appears only in such weird cases as this boundary condition, because the 45 will basically will have both normal and parallel derivatives on the inner boundary. So it is not a non-Neumann condition or the Rowan one. Okay, so our boundary value problem is now consists of the bulk operator, so the approximate twistor equation, so which I will call this approximate twistor operator by boldface L, and we also have a boundary operator boldface B, which I talked on the previous slide. I want to check whether the solution to this boundary value problem exists with the assumed asymptotic expansion of a solution 46. Where now in 46 we have this theta spinor theta A appearing, which is a formalized version of saying that this theta belongs to appropriate weighted L2 Sobolev space, where this subscript -1/2 basically says that theta decays faster than R to -1/2, which is consistent with the assumption about asymptotic decay, which I talked about a few minutes ago. So with the asymptotic expansion 46, we can actually rewrite our boundary value problem in terms of theta, not in terms of kappa. And so now our boundary value problem will have a form of 47, where now the operator is acting on theta, and I incorporated the parts from the principal part of expansion 46 into the right hand side of 47. Yeah, so now we have some FA and GA on the right hand side. And since I want to use a Fredholm alternative to prove the existence, probably the first thing to do is to find the adjoint of this operator, but fortunately here this operator is self-adjoint, which is probably another thing which convinces us that this choice of boundary condition is in fact natural. So yeah, so the Fredholm alternative now will have a following form. So the solution of 48 exists if and only if a specific integral with this source terms Fn and Ga contracted with this spinor V is 0. If spinor nu is 0, as in 49. So this nu is decays sufficiently fast at infinity, or belongs to the same weighted Sobolev space h squared -1/2, and is in the kernel of the adjoint operator to L and B. But since the operator is self-adjoint, then nu is just in the kernel of LB. And so the theorem that we managed to prove is that actually for this, if the inner boundary is a marginally outer troughed surface, or a MOTS, so if theta plus this expansion theta plus vanishes and the expansion theta minus is less equal than 0, then the kernel in this weighted Sobolev space is trivial. So there exists a solution. And the strategy of the proof was as follows. So first of all, we assume that this expansion theta plus vanishes. And we again considered another functional, which is just a composition of a symmetrized derivative of this element from the kernel nu and its Hermitian conjugation. So we know that this functional from the first line of 50 is greater or equal than 0. But again, since nu satisfies approximate twistor equation and decays sufficiently fast at infinity, this can be written only in terms of the integrand over inner boundary, and this integrand have the form of the one from second line of 50. So we can see that what's left is basically the other non-vanishing expansion theta minus and the one component of nu squared. So then if we apply a second assumption of a marginally outer trough surface, which states that theta minus is less equal than 0, we'll get, and remember that this functional that we started from has to be always greater or equal than 0, we'll end up with the fact that nu actually satisfies the spatial twistor equation, or that 51 is satisfied. But if we take into consideration that nu is decaying, nu lies in this weighted L2 Sobolev space, or that it decays at infinity, then from the fact that it satisfies spatial twistor equation, we'll end up with the fact that it has to vanish everywhere, actually. So the ultimate result here was that we showed that there exists a solution of boundary value problem 52, which is now re-expressed in terms of my original spinor kappa, and that the solution can be expanded ad infinity as in 53. So since we know that the solution exists, we can look again at the inequality with mass, which, let me remind you, had the form of 54, where high was just a partially contracted first derivative of the solution kappa. And now the boundary condition was that the high from 54 is just some freely prescribed spinor phi a on our inner boundary. So the goal, so now we can look at the right hand side of 54 and actually re-express or simplify it to get to and we'll end up that this inequality with mass actually has the form of 56, where now only the slashed derivative appearing in 56. So this is the intrinsic derivative to our two-dimensional inner boundary. But actually if we inspect closely the right hand side of 56, and this functional actually appeared in a lot of works about local masses with the use of spinors, and it even has a name, and it is called the Nestor-Witten functional. So since it has a name, I will call this functional H. So my ultimate inequality has the form of 57, where I just replace this integral with a symbol H. Yeah, so this Nestor-Witten functional it can be is given by 58. And so now a side remark for those of you who are more familiar in GHP formalism than is this abstract index notation for spinors. The Nestor-Witten functional can be written in the form 59. Yeah, so now we have our inequality with ABM mass 57, but the right-hand side of 57 actually depends on some freely prescribed spinor phi a. So now we can play around and construct some examples for specific choices of this spinor. I will just present here the two of such examples. So first one is a trivial one, because suppose that we say that this spinor on the boundary phi a just vanishes, and then this will yield the alternative proof of the positive mass theorem for asymptotically flat initial data with black hole inner boundary, because if we plug 0 as phi a in our Nestor-Witten functional, then we'll just get that m is greater or equal than 0. Second example, which is more interesting, is an example where we assume that the spinor phi is a solution of a two-dimensional Dirac equation with eigenvalue. That phi is an eigenspinor of a two-dimensional Dirac operator with eigenvalue lambda. So phi satisfies equation 60. Now, just by inspecting equation 60 itself, we can deduce that lambda has to be purely imaginary. And if we use this fact and plug such phi in the Nestor-Witten functional, we'll get two things. Firstly, we'll see that the terms with this eigenvalue in Nestor-Witten functional will cancel each other out. And secondly, we'll get that the L2 norms of the spinor phi has to be equal to each other, as in 61. And after some simplifications for this choice of phi, the mass inequality will have a form of 62, where we just have absolute value of the expansion theta minus and the square of one component of phi. But now this form 62 can be simplified even further if we use the fact that on a topological sphere, which we have here, each eigenspace of a two-dimensional Dirac operator is actually spanned by the eigenspinor phi together with its complex conjugation. So since we know that those spinors can form a basis, let me just normalize them as the basis should be normalized. So I will just assume that phi A and its Hermitian conjugation contracted with its Hermitian conjugation is 1, or in the components notation that the relation 63 is satisfied. Then, what if we plug the relation 63 in our statement that L2 norms of those components of phi have to be equal, as in 61, then we'll get that the square of phi naught is actually 1/2 of the area of the inner boundary. So we can use, as in 64, and we can use it to simplify 62 and ultimately get that the mass inequality in this case, that it will have a form of 65, where now we have this area of our inner boundary partial S. Of course, it's nowhere near the Penrose inequality because we're in the regime of Schwarzschild initial data. Theta minus is actually vanish, so it will end up again with proof of the positive mass theorem in there. Okay, so that was it. So during this talk, as we summarize it, so during this talk, I used a second-order spinorial equation to construct a new inequality with ADM mass of asymptotically Schwarzschildian initial data, and with the appropriate choice of the boundary condition, I was able to relate this mass integral to the Nestor-Witten functional on the inner boundary, which depended on some freely prescribed spinor phi A, and this freedom of choice can be used to construct some examples of inequalities which bounds the ADM mass of such initial data. As for the future perspectives, so first of all, we only considered one type of boundary condition here, which was probably most natural one, but this doesn't mean that the other ones shouldn't be considered. We could also try to include the angular momentum here, or to construct some inequalities with mass and angular momentum, but this would probably require the assumption that the asymptotic expansion of a solution of the approximate twistor equation is some slightly different form. And lastly, there is also there could also be a way to do something that Helsich did, but and by that I mean to include conformal transformations in the picture to construct even more general inequalities. Okay, thank you very much. That was it.
Thank you very much. Questions? So if you don't have questions, I have some. So beginning from this last slide, these conformal transformations of what? three-dimensional metric, four-dimensional?
Yeah, yes, a three-dimensional metric.
And but so you change initial conditions, or what is the?
Yeah, so what Hertzig did is he showed a positive mass theorem using the spinors, and then used a conformal transformation to prove this inequality, which was again almost Penrose's inequality, but with some coefficient in front of the area.
What about this Lichnerowicz equation? Can be somehow included, this method for vanishing mean curvature, that you start with one, yeah, you do this conformal transformation in order to satisfy the initial constraints, can be somehow related to this? Probably not easy, yeah. But
yeah, I'm not sure.
Some other questions? So I have second question concerning this. Now here you on this boundary you choose this function phi, yeah,
Yes.
to get as strong inequality as you can. Cannot you consider this as somehow variational problem, that you somehow vary this integral on the right hand side, and you are looking for solutions of this variation to be maximal integral?
Yeah, I guess we could, but actually we were kind of inspired by those other construction of quasi-local masses, which had the Lenster-Witten functional in them, and those constructions, like I don't know, the paper by Lionel Mason, they just kind of choose the equation for phi, and to get, I think they wanted to get a positive mass theorem, but yes.
But you understand, you have an integral, you have.
Yes, of course, I understand.
Integral, you vary.
Look for the maximum. Yes, that's definitely can be made.
Some other questions? Okay, if not, thank you again.
Yeah, thank you.
Okay, so